student, I am Latif sir. Today I will discuss about the first chapter of ISC Class 12 Chemistry, the solid state. On this topic, I have already uploaded one video. This is my second video. Today I will discuss about different type of crystal system, cracking fraction, and the calculation of density of crystal. Let's see. Crystal system. There are about 230 crystal system or crystal. There are 230 crystal forms which have been grouped into 14 types of space lattice. These are called Brabis lattice. So, what is Brabis lattice? There are about 230 crystal forms which have been grouped into 14 types of space lattice called Brabis lattice. Generally, a three-dimensional unit cell is described or represented by three axes. Here you can see A, B, C, and three interfacial angle alpha, beta, and gamma. Alpha, beta, and gamma. So, depending on the value of three interfacial angle alpha, beta, and gamma, and three axes along three direction A, B, and C, where A, B, C are the edge length along three direction of the unit cell, and alpha, beta, gamma the interfacial angle between these three axes. There are total 7 crystal system. So let's see that crystal system and the parameters of unit cell. You have to remember this relation between ABC and the angles alpha, beta, and gamma. 7 crystal system. First crystal system is cubic. In case of cubic crystal system, value of A, B, and C are equal. That is, edge length along three axes are same. A equal to B equal to C, and angles alpha, beta, and gamma all are equal to 90 degree. In case of tetragonal system, the value of A and B are same. That is, edge length along A and B axis are same, but along C axis is different. That is, A equal to B equal to C, not equal to C, and alpha, beta, and gamma all value are equal to 90 degree. Now, rhombohedral. In case of rhombohedral crystal system, the value of A, B, and C are equal. That is, where along three axes, the edge length of unit cell are equal, and the value of alpha, beta, and gamma not equal to 90 degree here. You have to remember. Number 4, orthorhombic. In case of orthorhombic unit cell, the value of A not equal to B not equal to C, but the value of alpha, beta, and gamma is equal to 90 degree. Number 5, monoclinic. In case of monoclinic, the value of A not equal to B not equal to C. That is, the axes along three direction are not equal, but the value of alpha and gamma is equal to 90 degree, but value of beta not equal to 90 degree. In case of now number 6, triclinic, the value of A, B, and C not equal are not equal. That is, edge length along three axes are different, and the angles alpha, beta, and gamma not equal to 90 degree. That is, the value of interfacial angles are also not equal. Now, number 7, hexagonal. In hexagonal unit cell, the value of A and B are equal but not equal to C, and the value of alpha and beta and gamma. Alpha and beta is equal to 90 degree. Alpha and beta is equal to 90 degree, but the value of gamma not equal to 120 degree. Value of gamma is 120 degree, and value of alpha and beta is 90 degree in case of hexagonal. So in the exam, the question will appear like this. You will provide the value of intercept, that is A and B and ABC, and the relation between alpha and beta and gamma. So, the question will ask that which crystal systems is it? Okay, so you have to remember the intercept and angles, the relation between them. Now let's see the 14 types of Brabis lattice. You should take a snap or a screenshot. 14 types of system, primitive units, primitive, face centered, body centered, end centered. The relation is given here, and the diagram is also given to the left, right. Just take a screenshot. And orthorhombic, monoclinic, triclinic. Here the crystal system, cubic. In case of cubic, uh, in case of cubic unit cell, primitive, face-centered, and body-centered all are possible. In case of mm, tetragonal unit cell, the primitive unit cell is possible and body-centered unit cell is possible, but face-centered and end-centered not possible. In case of hexagonal, only primitive unit cell is possible. In case of rhombohedral, mm, only primitive unit cell exist. In case of orthorhombic, primitive, face-centered, body-centered, end-centered, all are possible. All type of unit cell are possible. In case of monoclinic, only simple or primitive unit cell and the end-centered unit cell is possible. In case of triclinic, only simple cubic unit, simple or primitive unit cell is possible. So the count total, there is total 14 types of unit cell or Babbage lattice. Now cracking fraction. What is cracking fraction? Cracking fraction, it is defined the ratio of volume of the unit cell that is occupied by the sphere to the volume of the unit cell. That is cracking fraction is the volume occupied by the particles or by the atoms in present in the unit cell divided by volume of the unit cell into 100. Let's calculate the cracking fraction of different cubic lattice. Let's let the edge length of a unit cell is a. Then volume of the unit cell is a cube. Because we consider that unit cell is cubic, then the formula of calculation of volume is a cube. Now the occupied volume by the particles, constituent particles, depends on two factors: number of lattice point present in the unit cell and on the radius r of the atoms or particles occupying the lattice point. So, calculation of cracking fraction in primitive unit cell. In primitive unit cell, you have to remember that the atoms or particles are attached to each other along the edge. You can see the diagram to the right. This is a one face of a simple cubic unit cell. Here you can see that the atoms are attached to each other along the edges. So the relation between the edge length a and the radius of each particle r is r plus r is equal, that is 2r is equal to edge length a. So 2r is equal to a, then r is equal to a by 2, and number of particles per unit cell. In case of primitive unit cell, we know that this is equal to 1. So occupied volume is 1 into 4 third pi r cube, because 4 third pi r cube is the volume of one sphere, one particle. Then total one particle is present, so 1 into 4 third pi r cube, and the value of r is a by 2. So the occupied volume is pi a cube by 6, then cracking fraction is pi a cube by 6 divided by a cube into into 100% is equal to 52.36%. Now in case of face centered unit cell, in face centered unit cell, you have to remember, in face centered unit cell the particles are attached along the phase diagonal of the unit cell. In face centered unit cell, attached along the particles are attached al- in face centered unit cell, particles are attached along the phase diagonal of the unit cell. If the You can see the diagram right to the right. It is the one phase of a face centered unit cell, cubic unit cell. Here it is shown that the particles are attached along the phase diagonal, that is AC. AC. AC is the phase diagonal. And we know that if the edge length is A, then the phase value of phase diagonal according to the formula is root 2A. So AC is equal to root 2A, and from the diagram it is shown that if radius r of each particle, then r plus r plus r plus r, total 4r is also a phase diagonal. So 4r is equal to root 2a, then r equal to root 2 by 4a. And we know that number of particles in phase centered unit cell is 4. So total volume occupied by the particles by four particles is 4 into 4 third pi r cube. That is, and you have to put the value of r root 2 by 4a. Then total volume occupied by the particles is pi a cube by 3 root 2. Now cracking fraction. Now cracking fraction is pi a cube by 3 root 2 divided by a cube into 100 equals 74.05%. Now in body centered unit cell. In body center unit cell, you have to remember that the particles are attached to each other along the body diagonal of the unit cell. It is very difficult to draw the three-dimensional unit cell in a page on a two-dimensional page. That's why I have not drawn any diagram in case of body centered unit cell. But you have to remember in body centered unit cell, the particles are attached along the body diagonal. If the edge length of unit cell is a, cubic unit cell is a, then according to the formula, then the body diagonal will be root 3a and the face diagonal is root 2a. You have to remember body diagonal is root 3a. And like in the similar way, in case of face centered unit cell, r plus r plus r plus r, that is 4r is equal to, in case of face centered, 4r is equal to root 2a. Here 4r is equal to root 3a. 4r is also a body diagonal and root 3 is the body diagonal. So 4r is equal to root 3a. Then r is equal to root 3 by 4a. Now, in case of body diagonal, we know that, yeah, body centered unit cell, we know the number of particles per unit cell is 2. So volume occupied is 2 into 4 third pi r cube. That is, you have to put the value of r. Then we will get the volume occupied is equal to pi root 3 a cube by 8. So cracking fraction is pi root 3 a cube by 8 divided by a cube into 100%. That is 68.01%. You should take a screenshot of the calculation of cracking fraction in defined cubic unit cell. Now calculation of density of solid. The density of a unit cell can be calculated from its volume and mass. Density means mass per unit volume. So density of a unit cell can be calculated from its volume and mass. If A is the edge length of unit cell, then the volume of the unit cell is A cube. Now, if there is total Z number of constituent particles, Z number of constituent particles per unit cell. Hmm. We know that the number of constituent particles are different in different unit type of unit cell. Let Z is the number of a constituent particle per unit cell. Then the mass of unit cell is Z into m by Na, where m is the molar mass of the constituent particles and Na is the Avogadro number. So mass of unit cell is Z into m by Na. Now density of the unit cell is, density means mass per volume. So density is Zm by Na Zm by Na. Let one example. Question: copper crystallizes in FCC, that means face centered cubic lattice. FCC means face centered cubic lattice, in which the length of edge is 3.61 into 10 to the power minus 18 centimeter. Calculate the density of copper. So solution, and the formula calculation of density of solid is Zm by Na. We know that in case of face center, the number of constituent particles, that is Z, is equal to 4, and mass of molar mass of copper is 63.5. Molar mass of copper is 63.5 gram per mole, you can say. And edge length is given edge length A is equal to 3.6 into 10 to the minus 8, and the value of Avogadro number 6.022 into 10 to the 23 mole per mole. So put these values and you will get the value of density. Value of density will be 8.98 gram per centimeter cube.